Guys, please work out the first two examples that we have there. I'd like to find, please close your laptops, by the way. Kevin, it's going to be an intense week. We have 2 lectures on angular momentum and 2 lectures on rolling motion. Each is a question on the final. So out of this week, there's 2 questions on the final. We'll be reviewing a little bit of rotation and momentum and energy in the lecture on, we might be reviewing angular momentum too in the help session on Wednesday, in the review session on Wednesday. And the stuff that we're covering today is going to be reviewed in the review session next week. So please pay attention today. New concept, and also we have the extra lecture on Wednesday. So yeah, please wake up, guys. So before we continue with the topic of angular momentum, I would like us to calculate the moment of inertia of, this is a bar, thin bar. At the end of it, there is a point mass. What would the moment of inertia of this composite system be? And then once you're done that, please move on to calculate the moment of inertia of a thin bar of length 3r. And they both have mass m, by the way. The bar has mass m, and the sphere has the same mass m. What is the moment of inertia of these about the pivot at A? So take a minute, please, and do both. And then we're going to move on to angular momentum. Once you're done those, please stop copying until, I'll tell you it's okay. So please finish those first. So what I'm driving towards these 2 examples is the fact that the moment of inertia of a composite system about a given axis is made up of the sum of the moments of inertia of the individual components of the system. What we had applied to point masses applies to composite systems because of the nature of the moment of inertia. So I'm not going to go through it again, but we had that the moment of inertia of a bar about a center of mass like this was given as 1/12 ml squared. And when you went to calculate it about this, like that, we used the parallel axis theorem. Okay, I'm quoting the stuff that we did last week. I'm going to put it right on. I'm not going to derive it again. We had about this pivot here would have been 1/12 ml squared. About this, you have to use the parallel axis theorem, which says ICM plus MD squared. Since D was L over 2 all squared, it worked out to be I about A for the bar. The 2 components added up to be 1/3 M times H squared, if the height is H or length is H. And the moment of inertia of the mass, the point mass, is simply equal to mr squared. So we'll call this M2 if you want, this M1, M2, so plus M1 times H squared. Okay, that's the moment of inertia of that system. We need this for an example that we'll do right after introducing angular momentum. So all we need to know is that moment of inertia at, like masses at. Yeah. For this example, hold on your questions, guys. Give me a chance to finish this and then I'll answer your questions. For this system here, we have I about A of the bar plus I about A of the sphere. And for this part, I'm going to quote the result from last week. Again, that is 1/3 M times L is 3r squared, plus the moment of inertia of the sphere, second part, has 2 components to it. ICM plus MD squared. And, this is still 1/3 M into the height, or the length of the bar is 3r all squared, plus, in the case of the sphere, ICM is 2/5 mr squared, plus the, okay, for the sphere, we'll go ICM for the sphere is 2/5 mr squared, plus you have to apply the translation term to the parallel axis theorem, and this is plus the mass of the sphere times the distance between the two axes, which is 4r all squared. That's your composite moment of inertia, or a moment of inertia of the composite object. First, Kevin.
Does that still work there next to the Shells?
We're not there yet, dude. All right. Somebody else had a question before you, Mark. Because the way it's defined, if you look at the chart, that we had last week, the only one that was defined in terms of the full length was the bar. That's the way it's derived. The moment of inertia is given by 1/12 ml squared about the center of mass. Please take another look at it. Yes?
What if the points of masses were not on a straight line?
It doesn't matter. mr squared. Yeah,
Magnitude.
yeah, exactly. Just the distance squared. Okay? For the...
So if the sphere was here, attached to
We'll worry about that, you know. For now, for this specific diagram, the question was, what if the sphere was on Santa's head? Right? You know, then we'll worry about that then. For now, it's here. That's what that is for. If it's somewhere else, we'll measure the distance to the center of mass. And, you know, yes? Because we need the moment of inertia of the sphere about what? About A. It's equal to ICM plus MD squared. That is the parallel axis theorem right there. The moment of inertia of any object about an axis not running through a center of mass, some other axis, is equal to the center of mass moment of inertia plus the MD squared term. Yeah?
So the same thing is going for the bar, right? But you already simplified.
Yeah, the bar, we already went through that all of last week. We're not going to do it again. We know that the moment of inertia of a bar about the edge is equal to 1/3 ml squared from last week. Okay, if you don't know that, then I have other business to transact with you. Okay, you should really, it means that you're not reading the lectures at all, which is not good. You have to have some retention from, you know, since we covered it about 3 times, I do expect you to retain that, at least to read it the night before you come here. Okay? Yeah, whatever. Trust you. Okay, so this is a brief summary. We need to be able to do this. Should be a piece of cake, guys. Add moments of inertia, that's all. Summary of relation between translational and rotational variables. F equals ma becomes torque equals I alpha. K equals 1/2 mv squared becomes K equals 1/2 I omega squared. Work is F times distance. The work here, sorry, this is work as well. Thanks, Kevin. Please fix that, it's not omega. Work is equal to tau delta theta. Please fix it so it doesn't look like omega. Today, we have a new quantity to introduce, and that is the angular momentum of an object. So please wake up for this part. We are going to begin an example today, and I doubt we'll be able to finish it. We'll finish it, when do I see you again? Wednesday. It's very important now, guys. You see that, I want to bring it to your attention one more time. Some people have been asking me how to study. I went through that about 2 times after the midterm. But you need to focus on is rotation now. Rotation, torque, and rolling, and angular momentum. Begin with those. If you have extra questions about stuff from before, we'll tackle them after we do this stuff. Your final exam is based almost entirely on stuff from after the midterm. Not entirely, but almost entirely. So what you focus on is priorities. Rotation first, then you go back to the stuff from before. So now, guys, we have 2 weeks on rotation, 1 week on rolling, 1 week on a bit of week on angular momentum, and 1 week on statics. They're all torque based. Torque is going to be the most important topic you have on the final exam. these 4 weeks, you have to be awake. The pace that we're going at is pretty fast. We're introducing topics quickly. You have to be on top of them. You have to do the assignments and at least, learn from the quizzes, do the examples that we do here, come to the help sessions when I'm not sick, right, and don't have a flu, and do as much as you can, but please retain the lecture material from one lecture to another. Review it that night, no later than 12 hours after the lecture. 24 is already sketchy. You have to take a look at it. It'll help you a lot. Yes.
So will the final have law of conservation of energy?
A little bit, yeah. Yeah. Okay. So moving on, a new concept now is that of angular momentum. If you have an object of mass m moving at speed v, we say that it has momentum p in the amount of mv, and these are vectors that are parallel, and that will have an angular momentum about a point A in the amount of, please pay attention now guys, the angular momentum about the point A, and there has to be a point of reference for the angular momentum. It is defined as R cross P. It's a cross product. So R cross MV. So that's the definition. Okay. R is the distance between the point. So what does it depend upon, guys? I have an object moving here. Please pay attention now. The object has linear momentum. The linear momentum is given by mv. The mass is not going to change. The speed is the same. So you see it as having mv momentum. You see it as having mv momentum. You all see it as having the same momentum. But the angular momentum of this object depends upon what we are taking the angular momentum about. This thing will have an angular momentum about him in the amount of rmv, about him in r times mv times sine theta. So there is an r term in there that the angular momentum depends upon. The angular momentum of this object, despite the fact that it has the same linear momentum about all of us, is defined as some product between distance and momentum. Momentum is the same, but the distance from you to here is not the same as his distance from, there to here. So that angular momentum is not going to be the same for everybody. So the angular momentum of this, any object moving, please pay attention guys. Any object moving in a straight line has angular momentum. About what? About a point on the moon. It has a tremendous angular momentum about a point on the moon. It's given by what? Distance times p. What's the significance of that? We'll talk about that later. But we have this basic definition of an object that is not moving in a circle. It's moving in a straight line. Yet, we say that it has angular momentum about some given point. Any object that is moving in a straight line has angular momentum about some point that is usually non-zero, unless it happens to be here or there. Okay? So any object having linear momentum also has this quantity called angular momentum. We'll talk about the properties of angular momentum in a little bit. But now, remember the cross product. Do you recall what we said about cross product between two vectors? What matters in the cross product between two vectors? What do we consider only? Something we consider and something we discount. Only the perpendicular components matter. Okay? Only the components matter. The parallel components don't matter. They don't factor in. Because we're talking about things that generate rotations. And, so recall that. Let me write this then as R perpendicular plus R parallel. I'm going to break up my R into two components. One perpendicular to the momentum and one parallel to the momentum. And the momentum vector is right here. Well, that's P, right? So P is right there. Okay. All right. So what does that reduce to? In linear algebra language, the R is made up of R perpendicular plus R parallel. And this vector, we're taking the cross product of this with P. What is that equal to? Well, that becomes R perpendicular cross P plus R parallel cross P. Okay. And in this regard, R parallel cross P is what? R parallel to what? R parallel to P. Remember, the magnitude of a cross product is what? R P sine theta. Okay, that's, let's go back to what the definition of a cross product is. The cross product between two vectors, let's say, vector V1 cross V2 equals to some vector V. The magnitude of V is given by V1 magnitude, V2 magnitude, sine the angle between them. Okay, so what am I taking in this case? R parallel cross P, I am breaking up R into two components. One parallel to P, one perpendicular to P. The one that is parallel to P makes an angle of what with P? 0 or 180, right? In this case, 0. So that is identically 0, because theta is 0, sine theta is... So the only thing that survives out of this is R perpendicular cross P. Okay, so L vector is given by that. We have two issues with that vector. We have two properties that we have to deal with. One is the magnitude and one is the direction. The L introduced this way is a vector. So we can figure out the direction of that vector by using the right hand rule. Stick your hand out like that. That's your right hand rule. And that's the way we're going to do it. Who's shaky on this? Not sure about how to use this? Come down. Yeah, give me a hand. Brave man. Okay, please pay attention. Those of you shaky people, I know all of us are shaky on this. Do that, please. Yeah. Don't be afraid of me. Stick your arm out all the way. Now, move back yourself so we can see what the hell is going on. Hey, there is an order to things in a cross product. You have to follow the order, otherwise nothing makes sense. There is vector V1 cross vector V2. Which one is V1, which is V2? The thumb, there is an order. The thumb is the first vector in the product. Okay, what is the first vector in the product? What is the product? Here, R perpendicular cross P. Okay. The thumb is R perpendicular. So have to point the thumb along R perpendicular. Where is R perpendicular? Up. So is that good? That's good, right? Where is P? P is what? P. The index has to be the second vector in the product, and that has to be P. So where is P pointing? That way. What is that cross product now? L, which is the result, is the middle finger is pointing into the board. Okay? So if you're in doubt about this, please take a minute to do that. And if you feel, well, I'll give you a minute to come and make fun of you out here. No, he will never forget it now. If you want the same experience, please come down. Thanks. What? Right hand rule. Okay, so guys, the vector itself is given by the cross product, the right hand rule, and you only consider perpendicular components to make life easy. Okay, what does that reduce to then? Please pay attention. Magnitude wise, this is equal to, this means that L in magnitude is simply equal to R perpendicular times P times sine of 90, which is 1. So just R perpendicular times P. What's another way to see this? The magnitude of L vector is given by R P sine theta. So look here, please, guys. What is theta? What is the definition of the angle theta? Give me a minute. What is the definition of the angle? I'm not going to forget you. Put your hand down. I will answer you in a minute. Not now. You're answering my question? Holy shit. Well, yes.
It's the angle between the two vectors.
How do you take it?
You look at where the arrows are pointing, and you go tip to tail, and then you look at the angle between them.
Garbage. What am I looking for? The proper mathematical definition of theta. You go follow the first vector counterclockwise till you hit the second vector. So was he right? Counterclockwise, no, he wasn't right. Okay, sorry. So you go this way, that's the angle theta. However, for all intents and purposes, he is right. We take the smallest angle between the two, and this could be the theta that we're talking about, because we are separating what, guys? Separating the momentum magnitude from the angular momentum direction. We're using the right hand rule for the direction. We could take just deal with the magnitude up there. It's totally fine. Now, that's theta, therefore this is theta as well. And then r sine theta, if I'm focusing on r sine theta in this product, what will that be? R perpendicular. So that also reduces to r perpendicular multiplied by p. Okay? So we have a new variable. The variable is the angular momentum defined by distance times p. Okay? Fine. Take a minute, please, to finish copying. We're going to go into the example that I doubt we'll finish it today, but we'll give it a try. Just somebody brought up to my attention that we said omit angular momentum in the outline. Right? It was tentative, and we weren't sure if we're going to include it or not. Okay, we'll take it, but maybe won't test you on it. Right? Right? But the outline says that we're not covering angular momentum. Right, so we'll have to stick with that. I mean, it is a tentative outline, and we intended to cover it with you guys, but okay, fine. We'll do this lecture on angular momentum. It's good for you to know it, but we will not test you on it, okay? Yeah, we can't be adding stuff to the outline right now. It was my intention all along to do it, but there is other sections involved and we can't. So please we'll finish this today and go to rolling motion after.
So I don't have to know.
Eh?
I don't have to know. It's gonna get
Well, you should know it. Yes.
So is angular momentum is not going to be on the exam?
No, it cannot be on the exam, that's for sure.
What about quizzes and assignments?
We'll have to take it out. It's on the assignment next week, a little bit, but we'll have to remove it. Yes? What? Okay, let's still do the example that I had in mind. Guys, the reason we're humming and hawing about it is because of time, but also it has a lot of value for you guys. Why? Because the concept of the cross product has shown up about 4 times this term in terms of torque, in terms of rotation in general, and it's going to show up in statics, show up in angular momentum. That is the reason we are expanding or doing. Next year we'll probably have angular momentum for sure in the course. The reason on your assignment there is angular momentum questions. I'm going to leave them in there, but we'll put a weight on them of 0. Okay? So if you want to do them, it's up to you. They won't matter. The reason we're doing that, guys, because there is a continuity between the 2 courses, 105 and 106. In 106, half the course, magnetism, will be based on cross products. The reason we do so many topics of cross product is because going into your electrical engineers, going into 106, which is your first core course, first core course for your discipline, it is heavily reliant on cross products. I'm not concerned. I've always had the intention of covering it with you. If we're not going to put it on the final, that's okay. But please give it its due respect, because we will see it again next term. Okay, let's do a quick example. Okay, so you fire a bullet at this bar and it lodges itself. The bullet lodges itself here. The bullet lodges itself in the bar. would like to see how high does that bullet go after the collision. H is equal to what? Or delta H. So that bullet is coming in at 90 degrees here and lodges itself on the bar. How high does it go after the collision? Yes?
Is that a fixed point at the top?
Yeah, the pivot is up there. Obviously, that's where the pivot is. It sticks inside the bar, yes. Yeah.
Is it somehow going to be attached to the bottom of the bar?
It's going to strike the bottom of the bar and lodge itself in there. Boom. The bullet will be right in there. And bring the whole thing up.
So we have to use momentum.
Yeah, and conservation of momentum. Yeah, that's okay, guys. The extra lecture, we're now going to use it for statics, which we will need for sure. So that's fine. Okay, so can I say then that 1/2 m bullet v bullet squared is equal to m bullet plus m bar, which is m g delta HCM. Why not? What is this implying? That energy is conserved during the collision. Is that correct? No. What kind of collision is it? An elastic. So in an inelastic collision, we lose energy. We cannot conserve energy before and after, despite the fact that it looks good. Okay, gotta conserve momentum. Then obviously m bullet v bullet must be equal to m bullet plus m bar times VCM after. Yes?
So you want to do L1 equals L2, but
Why not P1 equal P2? What's the problem with that?
because you're obviously trying to trick us.
Indeed, very smart. Guys, if you want to conserve linear momentum, you have to conserve linear momentum going for every part of this bar, which takes us back to what? Moment of inertia. This is conservation of angular momentum. So despite the fact that we're not testing you on this, I think we will have it in as part of the course next time for sure. Okay, so L initial equals to L final. That is what we are going after. So what is that, guys? L initial is equal to L final. I mean, I'm concerned about this angular momentum of this object. What is the angular momentum after it starts moving? So the bullet strikes it and it moves this way with angular speed omega. Initial angular speed is omega. It begins to move with omega. What is the angular speed? What is the angular momentum after the collision? Angular momentum is what? I omega. What is I? The moment of inertia of this object. That's equal to the moment of inertia about A. So guys, whenever you write down angular quantities, you have to refer them back to the pivot. As it starts moving, it has angular momentum about the pivot at A in the amount of I A omega. What is I? The moment of inertia of this object is I bar about A plus I of bullet.
So wait, does L equal IW? I mean, you didn't say that anywhere. You didn't really show us that.
Didn't I? Okay, let's dial back one bit. Thanks, Kevin. Let's do it here. Those of you, some of you might have already guessed it, but that's fine. Guys, if you have a massless bar pivoted about point A and attached to a mass at the end. So this is, I was wondering why we have so much time. Massless bar, and this is the point mass. Please pay attention now. This point mass is going to move at, this is distance r here. This point mass is moving at speed v. Okay? Right? What is the angular, by virtue of the fact that it's connected to the pivot using a massless bar, that bar is going to also do what? It's moving down, but the bar will cause it to also rotate. So rotate at angular frequency, angular speed omega. So now please pay attention for a second. L, the angular momentum, is given by what? R perpendicular times P, which is the same as, the angle is 90, RP, which is R M V. V, however, is equal to omega R. Therefore, this becomes L is equal to R M omega R, which is the same as M R squared omega. That guy is I. Okay? That guy. So L is equal to the angular momentum of an object is equal to I omega. Okay? We have made the transition from a point mass moving in a straight line to a point mass rotating and getting this result. L is equal to I omega. Yes? Yes, we can now use the same logic that we used for torque a couple of lectures ago and for kinetic energy to show that this works for a point mass, it works for a collection of point masses and solid objects like a ring or a disk. This is okay for a point mass and okay for any object that has a given moment of inertia about a certain pivot or axis. So the new definition, or the resulting definition of angular momentum, is also I omega. So now we go from P equals to mv, P equals mv, the equivalent in rotation is L is equal to I omega. Okay? So thanks for that, Kevin. L is I omega. Fine. So an object that rotates, be it the disk, a point mass, whatever, its angular momentum is written as I omega. We have this bar coming in. Okay, this bullet coming in, hits the bar, and the bar begins to move. Now we have an object that has a moment of inertia I about A and is rotating. The object is made up of the bar and the bullet together, and they're beginning to spin at omega. Their angular momentum is given by I about A times omega, right there. What is that? That is easy. We just did that a second ago. 1/3 ml squared, and for this guy it's equal to m bullet times h squared. The length is h. Okay? Fine. So the question now, next. The question next. I'm really glad that I did not read the outline before I came today. Otherwise, we would not have covered this for sure. You need to know it. There's no, or know about it at least. It's not acceptable to leave this course without knowing about it a little bit. So that's fine. L initial. Okay, guys. Now we're hit with an issue of equating. Please bear with me. We're equating the angular momentum of a spinning object, which is fine. Okay, what is the angular momentum before the collision?
0.
Of that. Okay, guys? What is the angular momentum before the collision equal to? So we go from Pi equals Pf to Li equals to Lf, but that is for what? That's for a whole system, right? if there is no external forces acting on the system, angular momentum is conserved, as is linear momentum. We can prove it very easily. You go from one to the other, it's pretty easy. So now, after the collision, we have angular momentum. Before the collision, do we have angular momentum? Yes. Yes. None for the bar, but the bullet is part of the system too. Because the condition, guys, for conservation of momentum is that there should be no external forces. Okay? There is a force exerted on the bar, force exerted on the bullet. There is external forces on each, but as a system, the force between them is internal to the system. So the angular momentum of concern after the collision is that of the system, which is here. Before the collision is also that of the system, which is what? 0 for the bar, plus what? Plus the, for the bullet. Does the bullet, which is moving a straight line, does that have angular momentum? Yes. What is it equal to? It's equal to R cross P. R, P, sine theta. Well, this is a bit difficult because what is theta? All I'm going to do is wait till the bullet strikes the bar. And then P is here, right? And R is just H. So that's equal to the angular momentum before Li is, that guy is H times M bullet V bullet. Okay? Now, guys, so before the collision, we had the bullet was the only thing that had angular momentum. It's not rotating, it's not spinning, but by definition, angular momentum is distance times linear momentum. I about, or L about A. So since there is no external forces, we say that Li equals to Lf. We can prove that. We haven't done the proof for it, but we can do it easily. Okay, one more thing I want to go through with you. That's for some really cool demos that I'll hopefully get for you this week. By the way, to solve this problem, what do you do now? Guys, what do? We have an object. Please pay attention. You're not required to do this, but how do you do it in principle? Now that it's been brought up. You have a bar and a bullet with an angular speed going up. They have what now? They have kinetic energy in the amount of 1/2 I omega squared. Where is that going to go? Into gravity. Okay? It's equal to M1 plus M2 G delta HCM. You can figure that out on your own. Before I let you go, please pay attention here. L equals to I omega. Okay? As a vector, which way does it point? I've got a disk spinning. A disk is spinning at angular frequency omega. Omega is obviously a vector. Which way does it point? We could say that, that's fine, but it's not appropriate. For a vector, which way does the angular speed vector point? Please, the other right-hand rule. You go with the direction of spin about the axis, and where the thumb goes, okay, you spin this way with the right-hand rule, and where the thumb points is where omega is going to be. Because L is parallel to omega, then L is also going to be pointing along this direction as well. Okay, now please bear with me, last minute. We need this for the demo I'm going to have Ravid help me with in 2 days. L is equal to I omega. dl by dt is what? Please pay attention. dl by dt is I times d omega by dt if what? If the moment of inertia does not change. Okay? So that's equal to I. What is d omega by dt? That's I alpha. Okay? D omega. So what is that? What is that talking about? I alpha is what? Torque. Torque net or torque external. Guys, what is it saying? That the external torque on an object is equal to the change in its angular momentum. This is the equivalent of Newton's first law. What is it saying? If I have a disk spinning at a given angular speed, it will continue to spin at the angular speed unless you apply a torque to it to stop it. Please pay attention, guys. The disk is spinning. Let's say the disk is spinning like this. This is my angular momentum vector. If this is my angular momentum vector, which way is my disk spinning? This way. There's a disk spinning here. If I want to change the speed of spinning of the disk, angular momentum is a vector. dl by dt implies one of two things. I'm either changing the speed at which it spins, and I have to apply a torque to slow it down and speed it up. Also what? I can also change what for a vector? Direction. It's saying that if you have a bicycle wheel spinning here, and you want to tilt it, it's not going to be easy. You see that, guys? What this is saying is to slow down the bicycle wheel. How do you slow down a bicycle wheel? It's spinning. You apply a force of friction. The force of friction exerts a torque about the axis. That's easy. Speed it up, slow it down. We need torque. We need to spin it or stop it. But the concept that is baffling sometimes is, why do I need to exert a force? I mean, the wheel is spinning this way. If you want to move it this way or that way, to cause it to tilt this way, it takes a lot of torque to do that. And that's what we're going to see in a couple of days. You see how that works.